In this video, we will discuss some of the geometric primitives we need to talk about motion planning. We start with defining paths and trajectories. Let's say that X is the space in which we plan. A path in X is a continuous map P of S from the interval 0, 1 to X. The variable here is not t, which would be time, but the variable s, which is also called curvilinear coordinate. Note that there could be different functions P of S that trace the same curve. According to this definition, they are different paths. Sometimes when we say path, we mean all the paths that have the same graph. That is, paths up to reparametrization. A trajectory of length t is a continuous map from the interval 0t to x. Now t is time, and big T is the time it will take the robot to complete the motion. A trajectory has more information than a path. From a trajectory, you can get a path by forgetting the timing information, for example, by rescaling it from 0t to 0,1. We can now distinguish between two types of motion planning. In path planning, we only look for a feasible path, without the timing information. Path planning does consider the kinematic constraints, but not the dynamic constraints. An example of kinematic constraint is the fact that a differential drive like the ducky boat cannot move sideways instantaneously. In kinodynamic planning, we look for a trajectory, which is the path plus the timing information. In kinodynamic planning, we need to take into account also the dynamic constraints. This means taking into account the inertia of the vehicle and the power of the actuators. In terms of state space, in path planning, we consider only the poses, while in kinodynamic planning, we also need to consider the velocities. Depending on the platform, we might need to also model the internal state of the actuators to make sure that the trajectory is feasible. This more than doubles the dimensionality of the problem, but it allows to find more efficient solutions. The analogous situation for vehicles would be considering parking versus racing. For parking, you don't care that the maneuver is particularly fast. Rather, you care that the maneuver is safe, and maybe you want to maximize the distance to the obstacles. In this case, path planning is what you want. If you're trying to race optimally around a track, you definitely need to consider the dynamics. You need to think in terms of forces acting on the tires, and the limits of traction that allow you to increase or decrease the momentum at the right points in the track. A possible approach to motion planning that can work for self-driving cars is decoupling the problem of finding a geometric path from the problem of finding the timing information. One can first find a path using a path planning method, then given the path, find the velocity profile. A velocity profile is what you can use to get a trajectory from a path. It is a map from 0t to the speed that we use to move along the curvilinear coordinate. This approach might be desirable because it is easier to solve the two problems in sequence rather than the original problem. This kind of factorization works for self-driving cars, because if a path is kinematically feasible, you can imagine the car to be able to do it very slowly, so it is also dynamically feasible. Also, for urban driving, you don't care too much about the optimality of the plan in the sense of finding a minimum time trajectory. The main concern is with passenger safety and comfort. This approach will not work for other vehicles, such as drones, where the dynamic constraints are not negligible and the robot is under-actuated. A two-level planning approach works well for AVs because it tackles the two main challenges of planning separately. At the global level, the challenge is to navigate through a complex environment. This problem is very nonlinear. There could be multiple solutions that are topologically distinct. For example, there may be two ways to go around an obstacle. We call each bundle of paths an homotopy class. Two paths in the homotopy class can be deformed into each other without hitting obstacles. Once we have chosen the homotopy class, we can replace the environment constraints by much simpler constraints that essentially describe a tube in which the vehicle must stay. This allows to focus on the local challenge of finding dynamically feasible and efficient trajectories without also considering the complexity of the environment. In a typical two-level approach, a global planner computes one or more homotopy classes represented by tubes using path planning, without considering the dynamic constraints. Then a local planner is used to do full kinodynamic planning to obtain a dynamically feasible and locally optimal trajectory. In this video, we have seen the definition of paths and trajectories, and the difference between path planning and kinodynamic planning. We have discussed the pros and cons of a two-level strategy in which one solves the global problem kinematically and then does a local optimization to find dynamically feasible trajectories. In the next videos, we will look at how to formalize the details of motion planning mathematically in anticipation of studying solution methods.